do. Double field theory and duality. Thanks very much.
Okay, thanks very much, and thanks for the invitation to come back to Cambridge, to the Newton Institute. Okay. So I'm going to be talking about mostly about some work I'll be doing with Barton Zwieback and then later with Olaf Holm over the past few years. There's a number of different approaches to string theory, all of which have got different advantages and disadvantages. A lot of work is, of course, done in the supergravity limit, but that, of course, misses most of the stringy features, but although it's good for capturing the low energy structure of the theory. It can be thought of as string theory as giving rise to an infinite set of fields, and thinking about it as a field theory with an infinite set of fields is very interesting. But that misses some of the intrinsically stringy features. For example, it misses some of the duality symmetries. The traditional approach is using the perturbative worldsheet approach, which of course misses the non-perturbative structure. You could improve things a little by introducing D-branes, which includes some of the non-perturbative structure of the theory, and that can be understood in terms of modifying the perturbative, the worldsheet theory by introducing boundaries. There's also there's the matrix model approach, which is non-perturbative and has a lot of very nice features, but only captures one small region of the moduli space of the theory. And one thing which is interesting about this approach is that the geometry is hidden and perhaps emergent. And an approach which perhaps has not been used as much as has not been used so much is that of string field theory. The success of field theory in talking about particle physics led people in the early days of string theory to think that string field theory would be the way to go. But it's turned out to be much more complicated than people thought, and has a number of drawbacks. But nonetheless, it seems to be it's a very interesting approach which builds in the interactions of the theory in a very natural way and captures some of the exotic structure of string theory, and in particular incorporates the T-duality in a very interesting way. And some of what I want to talk about today came out from trying to understand what could be understood, what lessons could be extracted from looking seriously at string field theory. One of the problems with string field theory, particularly the closed string field theory of Barton Zwieback, is it's very complicated. And one of the motivations was to try and find a subsector of the theory which captured some of the intrinsic ingredients, but which was much more amenable. So what I'm going to be talking about, T-duality plays an important role. So this is familiar to most of you, I'm sure, which is the symmetry of string theory, which takes a circle of radius r to one of radius string length squared over r. It exchanges momentum and winding. It exchanges the coordinate x of the original circle with radius r to a coordinate x tilde of a dual circle. And so it can be thought of as acting on the doubled circle, which has got these two coordinates, and it could be thought of as a rotation in this doubled space. This extends to the case where you've got a d-dimensional torus, and maybe you've got a fibration of a torus fibration over some base manifold. So this would be a caricature of the space-time. So in here we'd be thinking about a torus fibration. So you've got a torus with coordinates x, and then a base space with coordinates y. We've got a metric and a B field which are constant over the torus, but whose values vary over the base space. So they depend on y, but not on x. And then in this is the standard picture of T-duality, which gives us a transformation which mixes the metric and the B field, and mixes momentum and winding, and changes the geometry and topology of this fibration. And in particular, its action on the metric and the B field is given nicely in terms of the matrix whose symmetric part is the metric and antisymmetric part is the B field. This is the D by D matrix on where D is the dimension of the torus. And this transforms under fractional linear transformations under ODDZ. So this includes the familiar transformations which take radius to 1 over radius, where the radius is encoded in the metric here, but also includes other transformations which include large diffeomorphisms on the torus and shifts to the B field. So when one looks at looking at string theory on the torus, the solution of the two-dimensional wave equation gives the left mover plus a right mover. And it's also useful to introduce the difference between these x tilde. So, and whereas x is conjugate to the momentum, x tilde is conjugate to winding number, and these are two-dimensional electromagnetic duals of each other. And in the free theory, this is a bit like introducing a dual potential for the Maxwell field, a magnetic potential dual to the Maxwell field. It's a useful thing to do. It's a nice formal thing to do, but it doesn't play any intrinsic and essential role in the theory. But in string theory, it's a little different. It turns out that in the interacting theory, x tilde plays a crucial role. This can be seen by looking at the vertex operators, which involve quantities like the exponential of x left or the exponential of x right, or in the corresponding string field theory, where Kugon's feedback showed that the string field necessarily depended on both the zero modes of x and the zero modes of x tilde. And this is essential for understanding the interactions in the T-duality symmetry. So in string theory, it's very natural and perhaps essential in the context of a torus to introduce these doubled coordinates, which transform linearly under ODDZ. There's been a lot of work, including some work by myself, on looking at the sigma model based on this doubled space, but that's not the line I'm going to take today. I'm going to be looking at things from the target space point of view, in the string field theory point of view. So if we think about strings on a torus, on the toroidal directions, they carry both a discrete momentum and a discrete winding number, both of these quantized. And the string, the string gives rise to an infinite set of fields which depend on both momentum and winding. In the familiar case where we don't have a torus, but in Minkowski space, you'd have fields which depended just on the momentum, and then you'd have an infinite set of higher and higher massive modes. We could also Fourier transform this to a doubled space. So these are both discrete coordinates, so their Fourier transforms are periodic directions x and x tilde. And so instead of having an infinite set of fields which depend on both p and w, we have an infinite set of fields on this doubled space. And so this gives rise to the construction from the closed string field theory of what I refer to as a double field theory, which gives an infinite set of fields which depend on both x and x tilde. I'll be going through this in a bit more detail by introducing some more careful notation, but this is just to give a general idea. And so we get a theory of an infinite set of fields depending on these double coordinates. And one of the and it's not quite a local theory in this doubled space. There's some subtle non-localities in this doubled space which are rather interesting. One of the questions we're very interested in is a question about constructing a theory for a subsector, for example, for a metric, a B field, and a dilaton, depending on these coordinates. And as we'll see, what happens is that these indices don't double. So this is still a D by D matrix, but this depends now on 2D coordinates. So the coordinate dependence is doubled, but the index structure is not. So the way this will work out geometrically is going to be will have to be rather interesting and novel. It will have to give some transformations which will reduce to the normal diffeomorphisms, but which will work in this bigger space and which will not be presumably will turn out not to be diffeomorphisms in this doubled space. So that's something more complicated. So we'll be looking at the double field theory on the doubled torus, or the doubled torus cross flat space, cross Minkowski space more generally. And we'll be looking, and it turns out that the general solution of string theory will involve sets of these doubled fields. So the kinds of solutions which we've been looking at in the past is only the tip of the iceberg, and there's really the general solutions will involve things of this kind. So in particular, there is important new kinds of backgrounds which necessarily involve these doubled fields. These are typically referred to as non-geometric backgrounds, and in fact, understanding non-geometric backgrounds like T-folds was one of the motivations for looking at this kind of structure. And one thing I want to stress is that this theory ends up with a real dependence on the full double geometry. The dual dimensions are not auxiliary or a gauge artifact, and that the double geometry is really physical and dynamical. And what I want to try and do today is try and give an introduction to how some of these things work. So as I mentioned, there needs to be a novel symmetry which reduces to the standard symmetries whenever the fields just are independent of half of the coordinates. And it should be done in such a way that it's covariant as to which half of the coordinates it's independent of. So that it should reduce to the normal, the familiar theory in the case where the fields are, for example, independent of this new coordinate x tilde. The familiar case of backgrounds depending on x are the ones which are probed by particles, where the ones depending on x tilde are the ones which would be probed by winding modes. The winding modes would see the x tilde dependence. And one of the features that emerges is that this double field theory captures some of the exotic and complicated structure of the interacting string. It turns out the closed string field theory is a non-polynomial theory with an exotic algebraic structure. It's not a Lie. The symmetry structure is not a Lie algebra, but it's based on something more general called a homotopy Lie algebra. And co-cycles play an important role in constructing this theory, so it leads to some stringy subtleties. This double field theory is set up in such a way that the T-duality symmetry is manifest, and so understanding issues of T-duality will be, this is a natural framework for understanding certain issues to do with T-duality, and in particular for constructing more general, certain kinds of non-geometric backgrounds such as T-folds. And one of the things which emerges is a generalization of the familiar T-duality to a more general cases where there are no isometries and so it gives rise to some generalization of T-duality where no isometries are needed. And there's been a lot of work in the past on sort of formalisms somewhat reminiscent of this, but the most closely related to ones are earlier work by Warren Siegel and Arkady Saitlin, which went some way to constructing a double field theory of the kind that I want to talk about today. So let me now turn to looking at introducing some notation and making some of these things a bit more precise. So we'll have a target space which is the space-time, which is a Minkowski space, an n-dimensional Minkowski space across a d-dimensional torus, and the total dimension will usually be I'll be thinking of critical strings, so I'll be thinking about a total dimension of 26 for the bosonic string and 10 dimensions for the superstring. And a lot of the formulae I'll present as if for the bosonic string, but there will be similar small modifications for the superstring. The coordinates of the space-time will be x mu for the Minkowski space part and xa for the torus part, and the corresponding momenta and the corresponding winding numbers in these directions. And I'll introduce corresponding coordinates conjugate to these winding numbers. So in the compact dimensions, we have the momentum and the winding number are discrete. They take values in an Orion lattice. Momentum is quantized and winding number is a topological quantity. And so the corresponding Fourier transforms will be periodic coordinates. So they're coordinates on this double torus. And in the non-compact dimensions, x mu and p mu in the Minkowski space are continuous. I will take the winding number in the non-compact directions to be 0, so that there's no infinite strings. And so I'll be restricting myself to things which have got finite energy. And so taking W to 0 means that I'm taking the fields to be independent of the corresponding x tilde mu. So I'm introducing an x tilde mu and a W mu in the formalism just because it simplifies a lot of the formulae, and I can use these indices I to run over all directions. But I'll be restricting myself to fields which are independent of x tilde mu, the auxiliary direction in the non-compact directions here, so that the fields will in fact just depend on the non-compact coordinates and then the double coordinates on the torus. So T-duality interchanges momentum and winding, gives an equivalence between theories on different geometries and backgrounds. And as Kugo and Svebak showed, it's a symmetry of the string field theory, provided the fields depend on both x and x tilde, the zero modes of the these two of the two string coordinates. So this is the usual coordinate and the dual coordinate. The usual T-duality rules are given for fields which are independent of the toroidal directions. So they're independent of xa and also independent of the x tilde direction. So it's just for fields which depend on x mu. And that gives the standard Boucher rules. Whereas what I'll be talking about today will be the generalization which involves fields which depend on both the toroidal directions, so that in particular shifts in the toroidal directions will not be isometries, and also on the dual coordinates x tilde a. And so this is the generalized T-duality that I looked at originally in a paper with a T. Stebelkar some years ago. So what does string field theory tell us? How does that give rise? So what does that tell us? Let's first of all think about what happens in Minkowski string field theory in Minkowski space. And so there's a closed string field theory worked out by Bart and Svebak. And there the string fields are functionals of loops x of sigma, loops in space-time, so they're functions on loop space. And also they depend on loops in a ghost coordinate, which I wouldn't say too much about here. And this xi of sigma can be Fourier transformed into a zero mode and an infinite set of Fourier modes, a center of mass coordinate and an infinite set of Fourier modes, which become quantum oscillators in the quantum theory. And expanding this out in the oscillators gives an infinite set of fields, an infinite tower of fields typically with more and more indices coming along. And as you go along the chain, the higher the number operators are for these oscillators, the higher the mass of the fields. And here, then integrating out the massive fields gives an effective field theory for the metric, the B field, and the dilaton, which starts off with the familiar Einstein-Hilbert term plus h squared plus grad phi squared, plus a systematic higher derivative corrections, with, depending on alpha prime. So what changes if we put the theory on a torus? The one change is that now x of sigma, when you expand it out, gives rise to both a center of mass and a dual coordinate x tilde of I, plus an infinite set of oscillators. And expanding it out will now give an infinite set of double fields, which will have exactly the same index structure as before, but now depending on both x and x tilde. And so one of the things we'll be trying to do is to seek a double field theory for a finite subset of these fields.
Okay, so the index I and j, I mean the graviton now does not give on the torus, right?
So it's not a tensor on the double torus, no.
I mean, because we have a kind of massless graviton on the flat space-time,
Yeah.
on the torus you don't have a massless graviton. So the index range I and j is restricted now on Minkowski space or on the torus?
Okay, so let's go back to the notation. So I runs from so if we're in 26 dimensions, I runs over 26 values, which will include, say, 4 non-compact directions plus 22 compact directions. And so...
I understand that, but I don't understand why your range of I and j in the graviton now is over the 26 when you compactify.
Okay, so once it's over the 26, I mean, the graviton... so
basically 10,
Yeah.
I mean 10.
Okay, 10. Okay, so the graviton is a 10 by 10 matrix, which when you're on a torus, you could of course do a standard Kaluza-Klein reduction where you get a metric on the four-dimensional space plus an internal metric, which could be thought of as a set of scalars. But I'm thinking about the 10-dimensional metric. But each of the tensors, you're right, can be, once you've got it on a Minkowski space across a torus, each of the fields I'm writing down can be decomposed using, all indices can be decomposed into mu's and a's. And if I was to do that, then there would be many, many more equations. So I'm not doing that just purely to simplify the presentation, but you're quite right that in interpreting the theory in 4 dimensions, one would do that, and the off-diagonal parts of the metric would be vector fields and so on. So
It's also, you're not throwing away Calusa climax. I mean, keep
I'm not throwing away anything yet, so it's
so it's even better to keep it.
yeah.
Presumably, how you truncate to G once you go higher up.
Yeah, so that's yeah. So far I haven't done any truncation. So the string field theory will give an infinite set of fields where the indices run over 10 values. They can be decomposed in this way. There's the latter way they can be decomposed, but the fields depend on 20 coordinates, or if all are toroidal, or if they're 6. So if we're in 10 dimensions, and if it's R4 cross T6, then it would depend on 4 plus 6 x's and 6 x tildes, so it would be in 16 dimension, 10 or 16 coordinates, but there would be 10 by 10 matrices. And so they can't be standard tensors on this higher dimensional space, so something different must be happening, and that's one of the things I want to explore. So any more questions before I go on? Okay, good. All right. So let's start by looking at the free theory, and let's look at the case where, let's put the background B field to 0. So I'm looking at the theory in a constant metric, which is an Minkowski metric cross some constant metric on the torus. And the string field theory, the string theory gives us two equations. So these are the equations which are for correct for the bosonic string. The intercept would be slightly different for the superstring. So we get that p squared, which is the sum of the momenta in the compact plus the momenta in the non-compact directions, plus the winding number squared, is given by the sum of the left moving number operator plus the right moving number operator minus the intercept. And the L0 minus L0 bar equals 0, has an n minus n bar on the right hand side. But in the presence of winding, there's a cross term which involves p dot w, which comes in here. So this one we can treat as a field equation, as a kinetic operator in the doubled space. So here I've got the constant background metric appearing. And this one in string theory is treated as a constraint on the doubled fields. So here we have an operator which is d2 by dx by dx, d by dx tilde, which is conjugate the Fourier transform of p dot w. And so we got an equation that this operator minus mu, where mu is the eigenvalue of n minus n bar, on a field equals 0. And this is what string field theory tells us to do. In some ways it's rather unsatisfactory that they're being treated so asymmetrically, but no one has come up with a good way of which treats them on a equal footing. One would like them both to arise as field equations perhaps, or both as constraints or something like that. But in the string field theory, the fields are required to all be annihilated by this, and then this gives rise to a field equation which is the dynamics. And this could be thought of as a Laplacian for a metric which on the doubled space which looks like this, and this could be thought of as a Laplacian for the metric of signature d comma d, which takes this form. So in particular, for the fields at level n equals n bar equals 1, we get a finite set of fields which satisfy the field equation that p squared plus w squared is 0, and that p dot w equals 0 on these fields. So let's think a little bit about this constraint. So we're looking at fields which are each field is constrained to satisfy this equation, where this value of mu will depend on what the number operators were, in other words, what the mass is. So if we go to momentum space, we get fields which are annihilated, which are eigenstates of this operator. So the momentum space has got dimension n for the non-compact directions plus 2d for the doubled torus directions. And this constraint, if it's p dot w equals 0, that defines a cone within this space, or if it's p dot w equals mu, it defines a hyperboloid within this space. So either way, this is defining, these fields will live on a space of codimension 1 in this double space. And the double field theory, the full double field theory describes a set of fields which live on these cones or hyperboloids with the extra constraint that the momenta and winding in the compact directions are all discrete. And one of the problems is that looking at such theories is that the naive product of fields which lie on the cone will not lie on the cone, or similarly from the hyperboloid. And for this reason, the vertices which arise in the interactions will need explicit projectors, and this is what happens in the string field theory, and this is what we're doing here will inherit from the string field theory. But there's a subsector of the theory, which is just a small subsector of the theory, in which looks much more like a conventional theory, and this is what I refer to as restricted fields. So these are fields which depend on only half of the torus coordinates, torus momenta. For example, conventional fields which are independent of winding, or fields which depend on the winding but not the internal momenta, or anything else related to these by T-duality. If you have a set of fields of this kind or of this kind, then products of these fields will also be of this kind. And that means that if one restricts to such fields, then no projectors or no co-cycles are needed. And the theory is much simpler. But here it should be stressed that this is just a small subsector of this theory. Here we have fields which depend on just n plus d momenta, whereas the full double field theory depends on n plus 2d minus 1. So the reason for talking about the restricted fields is this is the subsector where we can make a lot of progress in and do things very explicitly, whereas in the full theory things are much harder and progress has been much slower.
So question.
Yep.
You get 2d minus 1 because you're using the constraint where you have p dot w equals mu
Yep.
to remove 1 degree of freedom. But mu is nr minus nl.
Yep.
Roughly. So if I sum over all possible nrs and nls, won't that actually fill out the whole 2D space?
Yes, but the point is, it will fill up a lot of it. One has to. I mean, one of the things is when you're putting lattices together, there's a question about whether they build up the big lattice that you have in mind. But what's going on here is that for each field, any given field, there's a particular value of mu.
Yeah. But I'm just saying in the full string field theory, you should have all values in mu.
Yeah, but there's no field which depends on things for arbitrary values of mu. So each field will pick out one value of mu. But I don't know. Do you have some?
No, I'm just thinking if you've got the whole space. I mean, surely the space should be. Looking at the dimension of the space, and it's true. Each individual field for a given mu depends on that. But when you take into account all of the fields, and that includes all values of mu, and then you're just basically foliating your 2D plane with hyperboloids.
Yeah, but the thing is, there's no field which lives in this big space you're talking about.
Which lives in all.
And for the fields which I'll be concentrating on what I refer to as double massless fields, which satisfy p dot w equals 0. And there, all these fields live on the cone, and so we're just looking at fields which certainly live on this. And then with that, that's all that you get.
Chris, another question. I don't understand the nature of the restriction on the restricted fields. How can I declare just that I happen to be not interested in winding sectors and some such thing? I mean, if I have external states that don't have winding, then there'll still be winding sector states as part of the intermediate states. That's what field theory does, is that it goes off shell. So what's the nature of restricting? How can I restrict consistently to some such subsector? Okay,
that's a very good question. So the point is this. In the full theory, it's wrong to restrict. The full theory, in particular, when you're looking at the intermediate states, there'll be unrestricted fields going around in loops. So in the quantum theory, it's the wrong thing to do. One thing is that this is giving a closed subsector of the theory, which is a closed classical theory. So in particular, when we're looking at fields of this kind, these are the set of fields which will would correspond to the usual supergravity fields, for example, which would be the right things to look at which would be an appropriate thing to look at in a certain kind of effective field theory. But when one looks at the quantum theory, these fields would not be enough. In particular, there'd be winding modes going around in the loops, as you say. So this is this set of restricted fields is not what I'm interested in. It's just the part of the problem which is easy to do. And so I do it because it's doable, not because it's where I want to go. So it's a warm-up exercise for looking at the full theory.
Classic technique.
I apologise, but it's as far as we've got so far. So it's so to see some of the structure of this theory, let's look at the case where we have a torus background, a constant torus background with constant fields G and B. Here, these are the toroidal directions, these are the non-compact directions, it's Minkowski metric. And I'll take the background B field to be 0 as well, so that all of this is 0 just for simplicity. There were generalizations of all these formulae where I put this BAB back in. And I'll look at fluctuations where we have a fluctuation H in the metric and a fluctuation B in the B field, which fit together into a little e. And I'll define this derivative as being the derivative with respect to the dual coordinate, but the indices lowered with the metric. And if one was to look at the usual action for a metric in a B field without any dependence on the x tildes, we'd have this standard form of the action plus higher derivative terms. And if we looked at this, let me use L to define the quadratic part of this, the thing which is where you expand all these things out to quadratic order in these fields. And here I've introduced the field D, which is related to the dilaton phi by this combination. And the advantage of this field D is it's invariant under T-duality. Under the Boucher rules, phi shifts under T-duality, but just in such a way that it's compensated for by the shift in root det G. So this means that e to the minus 2D is a density rather than a scalar, but it's a useful variable to work with because it's D is a T-duality scalar. So to write the full double field, the quadratic part of the double field theory action, I'll write using in terms of the L, which is the quadratic part of this Lagrangian. And one gets something which is quite interesting. One gets a structure which is, so we're integrating over the doubled coordinates, as one might expect. We're getting the usual form of the action, the quadratic part we had from the quadratic part of the usual action which we had on the last slide. And here we have the T-dual version of that, where we're swapping partial for partial tilde, and we're taking the T-duals of the fluctuations H and B, which, since they're linearized fluctuations, just flips the sign to minus H and minus B. So here we have the usual action plus the T-dual action, which is as one might expect. But then there's a slight surprise in that there's some interesting cross terms which involve cross terms involving the metric and the B field and involving normal derivatives and the dual derivatives. So we get the action plus the dual action plus some strange mixing terms. And if we look at the symmetries, they're quite interesting. If these have two vector parameters, epsilon and epsilon tilde. And these transformations are symmetries of this, provided we use the constraint that the fields are annihilated by this Laplacian delta, and that the parameters are also. So if we look at this, we find that if we first of all look at parameters which are independent of x tilde, so that these derivative terms would drop and these derivative terms would drop out, we see that epsilon will be the parameters of linearized diffeomorphisms, and the epsilon tildes will be parameters for the B field transformations. But then we see that if we instead have dependence on the dual coordinates, these epsilon tildes, which were the B field parameters before, now become the parameters for linearized diffeomorphisms in the dual directions. And the epsilons, which had been diffeomorphism parameters before, now become B field transformation parameters. So what we find is that in the general structure, we're finding that the diffeomorphisms and the B field transformations are mixed and coming together on a very equal footing, which was rather surprising and rather gratifying. So all of these are somehow unified in this same structure. And so here we've talked about the quadratic action, and in the first paper with Barton, we looked at the cubic action for the full double field theory without any restrictions on the fields, and we constructed that explicitly to cubic order in these fields, and showed it's invariant under transformations which involve corrections to these transformations which are of linear order in the fields. So that was a very non-trivial construction, and we did it in two ways. One was by deriving it from the string field theory, and the other was deriving it through the Noether method, and we checked that they indeed gave exactly the same answer for the cubic form of the action. I won't say any more about the full cubic form of the action, but to say that it works out for the cubic one. It works out to be a fairly conventional kind of action, but from the quartic order and higher, we expect explicit projectors needed to deal with the fact that fields satisfying the constraint, products of fields satisfying the constraint, won't necessarily satisfy the constraint. So let's talk about the T-duality here. So the transformations of the background are familiar. I reviewed them at the beginning of this talk. They act naturally on the metric and B field on the torus, and x and x tilde transform as a vector under these transformations. So here, what I'm doing is I'm using a notation where I'm using all of the coordinates, but I'm implicitly restricting myself to ODD transformations which just act explicitly on the toroidal directions. So I'm using a notation where this looks like, in 10 dimensions, this would look like an O1010 transformation, but I'm only interested in the case where the O66 subpart of this is non-trivial, when I'm looking at a case where we're acting on a 6 torus, where little d is 6. So T-duality is a symmetry of the action I talked about, and that follows essentially from general principles, but it's very interesting working out how the actual dynamical fields, little e and little d, transform under these transformations. The transformations of the background we just seen, and the action is invariant if the field E, which is the metric plus B field fluctuation, and D transform in this way. So here we see that D, which in the usual case would be a scalar, is now an invariant under T-duality. Under these generalized T-duality transformations, it's transforming as a scalar. You've got to just have the transformation where the x transforms into x primed, acting linearly in this way. The usual Boucher rules would give that would be just for fields which are independent of the toroidal directions and their duals, and so there would be no transformation at all here. And here we're seeing when there is dependence on these extra coordinates, it will change momentum dependence for winding dependence, or dependence on x will be rotated into dependence on x tilde in general, or to linear combinations of dependence on x and x tilde. And the transformation of E is a little more complicated. Again, there's an x here and an x primed here. There's also some kind of tensorial transformation which involves these matrices M, which are made from the background E and the C and D subblocks of this ODD matrix. And these will be understood later as linearized forms of a covariant-looking transformation rule. And these are the transformations with both momentum and winding dependence. And they're indeed a symmetry of this action that I looked at. So as I mentioned, there's the naive products of constrained fields doesn't satisfy the constraint. So here L0 minus is L0 minus L0 bar, and delta was this constraint P dot W. More generally, I could have had a mu here and I could have looked at the case with mu's here, but again, there's a problem with the products of fields don't satisfy the right constraint. And the explicit string product has an explicit projection, and this leads to a lot of formal subtleties in the interactions of the theory. And it's partly this which leads to the symmetry not being a Lie algebra, but something more exotic, to do with the fact that that these projectors get in the way of various kinds of identities which one would like to have satisfied. And the theory also has non-local co-cycles in the vertices, and so the double field theory should also have these, which would give some subtle dependence on momentum, some subtle non-local dependence on the momentum occurring in these vertices. So maybe I'll skip the technical bit about the co-cycles. And what I want to do is I want to so we're going to be talking. So I'm going to be talking about at this stage to start looking at the restricted fields. So the picture is that the general double fields would depend on both x and x tilde. Conventional fields would depend on space-time would depend on x, and this is a null subspace of the doubled space with respect to this ODD metric, and T-duality would act to rotate this subspace to a different null subspace of the doubled space, and restricted fields will be ones which all the fields and parameters are restricted to such a subspace like M or N. So this has a lot of the advantages I mentioned, that the constraints are satisfied on all fields and products of fields, and that no strange non-localities are needed. The theory is T-duality covariant in the sense that it's independent of what the choice of N is, and so it can be written in a way which looks covariant. But the choice of N explicitly breaks the T-duality, if you're choosing fields which depend on X but not X tilde, that's clearly in a sense breaking the T-duality, but we can write the results in a way which is covariant. And this has the advantage we can find the full nonlinear form of the gauge transformations in the full gauge algebra and the full nonlinear action in this case. But there's the downside is that it's really, I mean, if we're just looking at this case, this is really just looking at a rewriting of the supergravity theory, because we're really just looking at fields which depend on X. And here we're looking at a dual form of the supergravity theory. So what we're buying in doing this is we're getting a T-duality covariant way of writing the familiar supergravity theory. But there's a sense in which this is a little disappointing in that we're not really getting any further than we would by just looking at the supergravity theory. So there's a sense in which it appears to be no directly new physics in looking at the restricted fields. But it does have an advantage that it gives some hints of the kind of structure which might be emerging in the full double theory, the one which lives on the cone rather than on the half-dimensional subspace. So for the remaining part of this talk, I'll talk about some of the structure which emerges for these restricted fields, which can be thought of as a way of rewriting the familiar supergravity theories in a way which is ODD covariant. So any questions before I go on to do that?
So if you just take a circle computation and you
Yeah.
have only two
Yeah.
double coordinates, and then in this case you can solve explicitly the level matching condition.
Yeah.
And, in principle, you can work in the whole sector of the theory. Have you thought about that?
Yes, yes. So that's quite an interesting case. So if you have just a one circle, so you've got, so P and W are just numbers. So you have the constraint that PW equals 0. There's just one, there's no dot here. So it means that either P equals 0 or W equals 0. So in that case, the P equals 0 part, the W equals 0 part looks like the familiar story of the familiar fields. The P equals 0 looks like a copy of that. So it looks like you've got two copies of the usual theory, except that the origin is double counted in that. So it's not quite that you've got two copies of that. And one could go some way in looking at understanding that case in more detail.
Well, I would think that can get more. Okay, let's
Yeah.
discuss it.
Okay, that would be interesting to discuss that later. But certainly there's looking at particular cases of one dimension or two dimensions are very good for understanding some of the looking at some of these things very explicitly. One of the problems is that one dimension is kind of atypical because the vectors just become numbers, and the thing becomes much more trivial. So So we're looking at double fields which are restricted to some d-dimensional null subspace. So it would be a 10-dimensional subspace in the case where the of the 16-dimensional case in the example I had before. So the first, so T-duality will act to rotate the choice of this subspace N. So it could be rotate one which depends on the x's to one which depends on the x tildes or linear combinations. So if we look at the background independent, it turns out that there are some background independent combinations of these fields which appear, in which the theory, it's natural to try and rewrite the theory. We would expect, so we have the background field capital E with the metric plus B field and the fluctuation little e, and we expect to start off with E plus big E plus little e. But that turns out not to be quite the right combination to have the familiar transformation properties and so on. And it turns out that this non-polynomial expression in terms of little e is the thing which I'll refer to as curly e, and which will turn out to be the correct background independent object, which will have the right transformations. So in particular, the symmetric part of this will be the full metric, which will have which will transform covariantly in the conventional way in the appropriate circumstances. And I'll use a ODD covariant notation where D is a total dimension. This would be O1010 in the superstring. So it'd be 10x tildes and 10 xi's. There should be a tilde on this derivative. And there's a natural ODD invariant metric, which is this, which is the thing which is used in constructing in order for constructions. So if we look at the generalized T-duality transformations, they act, the x is transformed as a vector, and the transformations of the dilaton are what, as we saw before, and the transformations of the fluctuations, the transformations we had before for the field little e, now transform into some very nice transformations for this total field curly e. And these take this form. So these look a lot like these, have a familiar fractional linear transformation form, but with the extra feature that now we've got x's here and x primes here. So it's a combination of a fractional linear transformation plus a transformation of the coordinates that they depend on. So this is a natural scalar, so this has got a natural scalar transformation under these T-dualities, and this has a rather natural form of these transformations here. And here, this, as I mentioned before, this works in the case without isometries. So let's get to that. And it can be rewritten in terms of what's sometimes called a generalized metric. On the doubled space, we can write a metric which has got, so this would be, if we started off in 10 dimensions, this would be a 20 by 20 matrix on the doubled space. And it's sometimes referred to as a generalized metric, but in this context, it's not really generalized because it's really just an ordinary metric on the doubled space. And so we have two metrics on this doubled space. There's the ODD invariant constant metric, and there's this one which is made up out of the metric and the B fields, which contains the dynamical fields. And so if little g was positive definite, this would be a positive definite metric. And if this little g had 1 time, then this curly h would have 2 times. And given two metrics, we need, there's a choice about which one we'll use to raise and lower indices. And I will use the convention that I'll always use this eta to raise and lower indices, which will be very convenient because it's a constant metric. So I'll define h with the indices upstairs, it's just given by raising the indices using eta. But it turns out that this h with the upper indices this way is precisely the inverse of the metric with lower indices. And this follows from the explicit form of curly h here. And we could go, conversely, we could start off by saying we've got two metrics which satisfy this constraint, and then the general solution of this constraint would be given in terms of a metric and a B field and can be written locally in this form. So a more covariant way of saying it is we've got two metrics satisfying a constraint which says that this is satisfied. And this form, one advantage of using this object is that this now transforms tensorially under the T-dualities. So if H is the matrix which gives the T-duality transformations, this curly H will now transform in a way which now looks like very much like a covariant tensor under these transformations. The action can be written in an ODD covariant way, in this way. And note that all of these indices are raised and lowered with eta. So this is really an action which is cubic in the metric curly H. And so we have this remarkable form that we've got a form of the action which turns out to be, apart from this e to this L, is something which is purely cubic in the fields, or plus a quadratic plus cubic in the fields, which is rather remarkable. And the gauge transformations have a nice form. They can be written in this way, which look a little bit like Lie derivatives. And I'll talk, one of the things I want to talk about is what the geometry of these transformations are, and the sense in which they can be thought of as a generalized Lie derivative. So this is the standard form of a Lie derivative plus two extra terms, one here and one here. I'll talk in a moment about what those terms mean. So if we look at the generalized Lie derivative, if we had, this could be used to define tensors with arbitrary numbers of lower and upper fields. Let me choose one lower and one upper in this way, which would have these transformations. We can write it in terms of the conventional Lie derivative plus two extra terms. One here, which has got some hidden metrics in, which are raising and lowering the indices. If I put it in explicitly, it's this term. An extra term here, which can be written explicitly with the metrics put in explicitly as this term. So we've got the familiar Lie derivative plus some terms which depend explicitly on this extra metric eta. So we have because we've given a space-time which has got this extra structure of this extra metric eta, we can write down more general things in these transformations. One can also define a generalized scalar curvature.
If you go to the Lie derivative before,
Yeah.
if you take the commutators, what you get?
That's a very good question. That's one I'm going to come to after the next, in a couple of slides. So one of the very interesting questions to look at is what happens to the gauge. What does this mean? Can we understand? How can we understand the gauge algebra in terms of these, and what does that give? So I'm going to say quite a bit more about the algebra of these things in a moment. But before that, I just wanted to say that the action can be written in terms of an object R, which is a natural object called a scalar curvature, which was related to what we had before by some total derivative terms. And then this transforms nicely as a scalar, and this is a density under these transformations. So there's a nice way of writing things in that way. So before turning to George's question, I'll just say a little bit more about the action that we had. So this was the action. So this derivative involves both normal derivatives and dual derivatives. And as before, we could expand it out in terms which have got two normal derivatives, two dual derivatives, and a mixed term. So the term which just involves two normal derivatives, you can rewrite in terms of conventional fields, and it gives precisely this action plus a surface term. And so we can use, so S naught is just the usual action but written in terms of these variables. And S2 is just the T-dual version of that, where under T-duality in all the toroidal directions, it takes the full curly E and takes it to E inverse, takes the derivatives to the dual derivatives, and takes D to D. And S1 is the covariant form of the strange mixed terms we saw earlier. So we're looking at the restricted double field theory where the fields are independent of half of the coordinates. And as I mentioned, if they're independent of the x tilde, they're equivalent to the usual kind of supergravity action. But it's been written in a duality covariant way where the duality changes which half of the coordinates the theory is independent of. It turns out to be equivalent to a version of the theory written down by Warren Siegel some time ago. And it's written in a way which is naturally adapted to talking about non-geometric backgrounds. So now I want to turn to George's question and look at the algebra of these derivatives and the relation to the gauge algebra. So if we take the two parameters, epsilon and epsilon tilde, and put them together into a 2D dimensional vector, then the gauge algebra will define a bracket for these parameters, which I'll refer to as the C bracket. And these generalized Lie derivatives also have the same transform with the same bracket, but with a minus sign here. And this bracket is starts off with a conventional Lie bracket, which is what you would get if you were just dealing with diffeomorphisms in the doubled space, plus a term which involves explicit dependence on these metrics eta. And this same form of the commutator was exactly the form of the gauge algebra found in a similar context earlier by Warren Siegel. And if we take these parameters and restrict to some subspace n as we were talking about doing, then that gives a natural decomposition of this 2D dimensional vector into a conventional vector plus a 1 form on n. And when we do this bracket reduces to precisely the courant bracket on n. So, this is a bracket which arises a lot in some of the mathematical literature. And here we're seeing that this approach here is giving a covariant form, a natural covariant form for writing down this bracket. So one of the strange features about this bracket is it doesn't satisfy the Jacobi identities. So both the C bracket, as I defined it, and the corresponding courant bracket don't satisfy the Jacobi identities, which raises the question about how this bracket can be realized as a symmetry algebra, because if there's a Jacobiator, the thing which you define by the double commutator plus cyclic permutations, then if one looks at a set of transformations, then because these are transformations acting on an action, this should automatically be 0. But on the other hand, using the gauge algebra, it turns out to be the transformation with respect to this Jacobiator. So there's a question about how that can work out, and it's rather interesting the way the theory manages to resolve that. It turns out the symmetry is reducible. We know, if we look at those two-form gauge transformations where you have delta b equals d alpha, and alpha, which is closed or exact, will give a transformation which doesn't act on the B field at all. So really the parameters are not one forms, but it's really one forms modulo closed one forms. And in this double field theory, the parameter this appears in this way. Parameters which are of the form eta times the derivative inverse metric times the derivative acting on some scalar will leave all of the fields invariant. And the resolution is that the Jacobiator turns out to be precisely the kind of transformation which doesn't act on the fields. So when you're looking at the gauge algebra, we're finding that the left-hand side, which should automatically be 0, acting on the fields, gives a transformation which turns out leaves all the fields invariant, and so there's no contradiction. And finally, I should mention that one can define another kind of bracket, which we call the D bracket, which is given by this generalized Lie derivative. And this is something which, so the notation is quite convenient, because when you restrict to a null subspace, the C bracket becomes the courant bracket, and the D bracket becomes another bracket which appears a lot in the mathematics literature, which is the Dorfman bracket. And with this restriction, the generalized Lie derivative becomes precisely the generalized Lie derivative looked at in a similar context earlier by Granier, Minasian, Petrini, and Waldron. So some of these things we've been seeing, some of the structure of the formulae we've been seeing are very similar to something which is known as generalized geometry, which is an approach to geometry introduced by Nigel Hitchinen and worked on by a number of people, including his student Galtieri. And in this one doubles the tangent space. In this one studying a metric and a B field on a conventional manifold. But it's useful to look at doubling the tangent space and looking at trying to understand the fields in terms of natural structures on this doubled tangent space. And in doing this, it leads to a way of formulating the theory in which has a natural action of the continuous group ODD. This is rather different from what we're doing here, but formally with some formal similarities. What we're doing here is we're doubling the space, the manifold itself, not just its tangent space. We're doubling the coordinates. That, of course, involves doubling the tangent space group, which doubles the tangent space to precisely the doubled tangent space that was here. But in this doubled field theory, the T-duality is plays a crucial role, and it's the discrete T-duality which I've been focusing on, which is the symmetry of the string theory, not the continuous T-duality, which acts on the continuous group, which acts naturally in this generalized geometry context. And in the context of looking at the double field theory, it really is the discrete group which is relevant. I mean, one way of seeing that is that it includes the ODD group contains the subgroup GLDR, which acts on as diffeomorphisms on the coordinates, and the periodicity of the coordinates breaks that down to the mapping class group of the torus, which is GLDZ. So it's crucial that in this context it's really the discrete group which is playing a role, whereas here it's the continuous group which is acting on the tangent space. But nonetheless, because doubling the space involves doubling the tangent space, a lot of the tensor structure is very reminiscent of the structures which are found in the study of generalized geometry. So there's some very close relations between the two. This is a natural way of, the generalized geometry is a natural way of extending, studying both a metric plus a B field on a normal manifold with a natural action of the ODD group. This has a natural generalization to what I refer to as extended geometry, which have a metric plus a three-form gauge field and an action of the exceptional U-duality group. And this is something which I looked at and then was followed up by some work with Pacheco and Waldron. And there's been, and one could attempt to try and look at rewriting the 11-dimensional supergravity theory in a duality covariant way in terms of such extended geometries, trying to look for a generalization of the double field theory that I've been talking about. And there's been a lot of work on that, initially by Hillman and then later by David Berman and Malcolm Perry et al. But presumably you've heard some of that in other talks here. So to conclude, the double field theory is constructed in terms the unrestricted double field theory. We constructed a cubic action for the full fields G, B, and D. For the quartic and higher, there should be interactions should have many features of the string field theory, in particular some of the strange non-local features. And one question which is still remaining is the issue about, is there really a fully gauge invariant unrestricted action for G, B, D alone, or are all the extra massive fields needed? And the evidence so far is that there's a lot of things which could have gone wrong already in trying to construct the cubic action. And the indications are that there seems to be no obvious obstacle to finding such a theory, and which would give some kind of effective theory for these fields alone. But it's a subtle question because it's not quite a truncation of the full theory, but it involves some integrating out of certain other fields. So the status is still not understood. But this double field theory has many advantages. The T-duality symmetry is manifest, It enables us to address certain stringy issues in a simpler setting than the string field theory. The last part of the talk I was restricting myself to the restricted double field theory, and there it was possible to look at the nonlinear background independent theory and construct it completely to all orders. There's been a lot of recent work, including works on, since then, including works on supersymmetry and on type 2, including Ramond-Ramond fields. There's been a lot of work on understanding the geometry, but I think there's still some questions remaining about understanding this at the deepest level and trying to understand what the geometry behind this double construction is. But there's been some very promising work in that direction, which I think is by Dan Waldron and collaborators, which I think could well give a good understanding of the meaning of this. There's also been some work recently in trying to explicitly use this for non-geometric backgrounds. I mentioned that as one of the motivations, and it would be very interesting to understand that, to explore that further. One of the features which has been one central feature here is I've been restricting myself to spaces which are tori, and one of the reasons for that is that in the case of a torus background, we understand the duality symmetries very well, and we understand T-duality, and we understand explicitly how to do the solve string theory explicitly in that background. It'd be very. I should stop. Okay. Well, this is the last slide. I've just got these 2 points to say. Let me just finish this this point, and then I'll stop. But if I was to look at more general space, we also understand duality in certain other cases. I mean, where we understand how to solve the string theory quite well. For example, in the context of Calabi-Yau manifolds or Vesamina-Witten models. But for general spaces, it's not at all clear what the story is. It's not at all clear whether or not there are duality symmetries which work in more general case for general spaces. Whether the duality symmetries we understand in toroidal backgrounds as the remnants of some bigger structure in other spaces, and it seems as if the doubling story seems to be very specific to tori, which have the same number of 1 cycles as they have of dimensions, and which is something that's not true for more general spaces. So a very interesting question is how much of what if anything implications this might have for understanding string theory in more general spaces. But that's something for the future. I think it's very interesting that just understanding string theory in detail on the case of a simple flat space across a torus actually turns out to have a surprisingly rich structure, giving rise to a double geometry which appears to be both physical and dynamical. And it'll be very interesting to see how this story develops in the future. So I'll stop there. Thank you.
Questions?
We're supposed to start with some latest string theory and S5 ring.
Sorry, say that again. Sorry?
Latest string theory.
Little string.
Yeah, and compactifying on torus.
Yeah.
And we believe that the theory in the lower dimension, low energy effective theory, still preserves 4D symmetries, right?
Yeah.
Can you do, I mean, if you use this double field theory formalism, can you learn something about this string theory compactifying on torus?
Yeah, that's a very interesting question. And I think, one of the issues is that, to really attract that, I would want to see, an explicit formulation of this little string theory, and that's one thing which, although there's a lot of implicit constructions, the explicit construction one you could actually do things explicitly is still missing. But I think if one could write, in principle there ought to be a string field theory for the little string theory. If one could write that down, then one could immediately start applying all this to that. So it'd be very interesting to see whether this could be useful. We could turn that around and try and see whether this story could be useful to trying to understand little string theory in detail. Okay, thanks.
One question. What about the open string sector?
The open string sector?
Yes, you have difference and is it like this street?
Yeah, that's a very good question. That's something which I didn't have time to talk about. But what happens is that one can understand D-branes in this story quite nicely. What happens is that the T-dual of if you've got a string which satisfies Dirichlet conditions, its boundary conditions, its T-dual will satisfy Neumann boundary conditions and vice versa. So that means in this doubled space, precisely half the directions will be Neumann and half will be Dirichlet. So you have a picture in this doubled space that all D branes would correspond to essentially to branes which are half-dimensional, which are Lagrangians, wrapping Lagrangian submanifolds. And what would happen under T-duality is you'd be rotating the subspace, which is the physical space, and so as the physical space rotated against the D-brane space, you'd see more or less D-brane dimensions, and you'd see effectively the dimension of the D-brane changing by 1 each time you did a T-duality.
I see. So, how a case where you have many D-branes, many kinds of D-branes, like intersecting D-branes? It's a D-brane system. T-duality acts very on like spherical areas and all of those are T-duality.
Yeah. That's a good question, and that's something which that hasn't been looked at yet, and it'll be interesting to see what that happens as well.
I comment on that.
Yeah.
So the section condition is like a half BPS condition.
Yeah.
So you can see all the half BPS things, which include ordinary D-branes. When you have intersecting D-branes, that's coarse BPS. So that won't actually solve the section condition.
Yeah.
So you need to go beyond the simple section condition of
Yeah.
one duality frame to see the intersections or branes with low supersymmetries.
Okay, good.
Okay, let's thank the speaker again. And before we do that, Prosecco time at 5 o'clock.